I hope that you can see my slides. Is it
Yes,
visible?
I see your slides, but not yet in presentation mode. Please put it.
Yeah. Okay.
Yes.
Is it okay?
Okay, perfect.
Thank you very much. This is a few requests before begin the presentation. Okay, let's start for the presentation. First of all, going for the objective of this work. My research work is, the aim of this research work is to fabricate high entropy alloys by using additive manufacturing method. I will give you each and every explanation related to each steps. What is additive manufacturing? What is high entropy alloys? And later I come to what are the things I did for my research and what are the research we gained. Okay. And first of all, I'm going to tell you about additive manufacturing. I think everybody is familiar about additive manufacturing. This one is one of the most promising method for this manufacturing for this era, because now we all know that this era is the era of sustainable manufacturing. Sustainable manufacturing is nothing but we are going to eliminate the wastages. So one of the best method for adopted to eliminate the wastes is additive manufacturing. Additive manufacturing, otherwise called as 3D printing. It is nothing but we are generating a solid or 3D object from a design, that is a 3D model that designed by using CAD software. And from this design, we are producing a solid model. This is simply an additive manufacturing. Let us give you a basic or one of the most promising and most versatile and used additive manufacturing method, that is fused filament deposition method. This is the very simplest method in additive manufacturing method, and probably that is not the method we use for our researchers. And fused deposition modeling is nothing but from a wire spool. The wire spool is fed to a nozzle, and before entering to the nozzle, this spool or the filament is heated and melted by using a heating agent. And when the material is molten, the nozzle move three-dimensionally. That means mostly the move nozzle move in XY direction, and the fusion or this bed move the Z direction. And by moving the coordinating this X, Y, and Z movement of this bed and this nozzle, we creating layer by layer product. And by using this layer by layer formation, we creating a 3D model. Let us see what is high entropy alloys. I know that everybody is familiar with alloys. We all know that what is alloy is from our school itself. We studied about what is an alloy, what is the peculiarities of alloys, what are the promising or what are the benefits of an alloy. And so while we comparing from a normal alloy to a high entropy alloy, what's the difference between high entropy alloy and a normal alloy? If we come with one of the best using alloy is steel. We all know that we are using iron and we're using particular element, chromium or carbon or different content, to improve the quality of that particular metal. That means if we, in a normal alloys, we are using another material in a particular amount to enhance the quality of the parent metal. While we are come to high entropy alloys, it's an entirely different thing. That means in high entropy alloys, we are using more than 5 or more elements, and in mostly in equal ratio. That means here there is no one is acting as a parent metal. Each and every metal is combined together to form a new alloy, which having a superior quality compared to all the basic metals. That is called as high entropy alloys. And let's go to my research. While I'm preparing the 5 elements, that is cobalt, chromium, ferrous, nickel, and molybdenum. These 5 elements we are used to prepare the high entropy alloys. And we are not able to feed directly this metal to additive manufacturing or the additive manufacturing feeds nozzle, because the grain size or the size of this material or the element is, we need to be in uniform size and mostly in spherical size. That's one of the demerits of additive manufacturing, and also we can call it the merits of additive manufacturing, because due to this property we get the maximum or the better surface finish. And what I will go and discuss about what are the methods we adopted to make or make the material in a uniform size. That means we are using cobalt, chromium, ferrous, nickel, and molybdenum. And while using these all metals, we need to make almost in the same spherical size. And first of all, we use a high energy ball mill apparatus. It's a mechanical process. By using this process, we high energy ball mill, we ball mill this entire material in a container and for 48 hours and to 3 days, up to 3 days. And after we find out that this materials is not what we accepted. That means the output of this product from the ball mill is not, we are not able to use directly to an additive manufacturing. So again, we used it for gas atomization method. Gas atomization method is nothing but by using a argon gas. For our experiments, we use argon gas. Using a argon gas, we heated argon gas and we sprayed this metal in a molten material to a substrate and received this material. You can see the image over here, microstructure of this. In the same image, you can find that still it's not in spherical shape. Some of the parts are some debris is visibly over here, and some of the material are not in spherical shape. So if you are using this material for additive manufacturing, you never gain a better surface finish. And obviously, this debris and this non-uniform materials make some defect. That means cracks, maybe some porosities maybe happens. These all defects may be happen. So again, we take in for another method, that is plasma spheroidizing. Plasma spheroidizing is nothing but this molten metal is taken for a plasma, and while we are subjecting this plasma state and after cooling, we get almost spherical shape. And most of the elements are not in equal shape, but most of the elements are in spherical shape. So we can take this for additive manufacturing. Let us say what is the method we adopted for our high-entropy alloy additive manufacturing. This is direct laser deposition method. You can see in this image what is direct laser deposition is, and there is a focused laser over here, and from this nozzle itself, this powder is spraying, and this is shielded by a argon gas, and while this powder is coming out through the nozzle, it's melted by the laser beam, and each layer is formed by this molten base metal. Clear? And these are the parameters we adopted for the our experiment. The laser power we adopted from 1000 watt, 1200 watt, 1400 watt, and we used remaining all elements as a constant. That is, scanning speed is 400 millimeter per minute, beam speed is 4 millimeter, feed rate is 8 grams per minute. And by using these parameters, we fabricated three materials, that is 1400 for 8, 1200 for 8, 1400 for 8. By using these three combinations, we make three subtract, and we conducted or taken that for mechanical testing. This one is the mechanical testing we conducted, and from this tensile testing, we found out that at 1200 watts, it gave the maximum tensile strength, that is 987 megapascal we received. And also we've taken this better one, that means the second sample for scanning, and by using optical microscope, you can see over here. I have marked here between three layers. It is three areas because in one area is this one is the first area as showing over here is G, that is equiaxed. Equiaxed, that most of the grain structure formed is very fine and very equiaxed. And here we can just the H area. The H area is nothing but this area. In H area, this dendrils is formed. Dendrils is nothing but when the temperature is high. That means while the 1200 watts, the temperature given by the in particular region is very high. And I also told that this is a high entropy alloys. There is more than 5 element is used. And when the temperature hits in some region, some dendrils may be formed. And obviously, we all know that equiaxial grains giving much better tensile strength. But here, dendrils form give a higher mechanical property and a high corrosion resistance property. But in case of high-entropy alloys, these all maybe happen in the same structure. That means in the same object, we need equiaxial and dendrites. And this is the more zoomed version of this H area. You can see how Then there's columns and black and some defects over here, some fractions, and these are the fine grains from this equiaxial region. That is, from G region, the more focus we is given here. For the H, the dendrils is visible here. It's in a, just like lines. Here it's just like a small modules. And this one of these are the corrosion properties. We conducted the potential damage correlation test for these metals and compare it with another three metals. That is another alloy. It's not a high entropy alloy, copper, chromate, ferrous, nickel, and normal stainless steel 316 and 304. And by comparing these all things, and sorry, we use the material is 3.5 weight% of salt and 1 mole of sulfuric acid. And in these two mediums, we conducted and find out that this material, what we fabricated using additive manufacturing, shows a superior quality of corrosion resistance. You can see over here. This one is the first one is showing that the high entropy alloy. And from these results, we concluded that we can fabricate a high entropy alloy using additive manufacturing. And the structure we find out that is a face-centered cube structure. And while we increasing the laser power, more and more columnar grains is found. That means when increasing the laser power, the columnar grains is increasing, and up to some extent, that means up to 1200 watt, it enhances the mechanical property. After that, the mechanical property drops because the size of the dendrils is enhancing and the amount of fine grains is decreasing. Due to this decrease of the fine grains, the mechanical property is reducing. And for the mechanical testing, we find out that the highest strength of the metal gain is 928 megapascal. And let's go to corrosion testing, and we find out that compared to other all metals, this high entropy alloys having a superior corrosion resistance property. These are some of my references. Thank you. If you want to know more about my research and my articles, you can log on to these whole things. If you have any queries, you are most welcome.